Now we're going to try to use this result, to get an actual result for flow over a plate. So let's take a look at a simple plate. It's 2 meters long. We're going to ask how big is this viscous boundary layer for a 2-meter plate with airflow if the flow is traveling at 1 meter per second. So to do that, we're going to use the formula we just identified. This is the exact formula for the size of the viscous boundary layer as a function of x. Delta over x equals 4.92 times the Reynolds number to the negative 1/2. So to solve this, the first thing we're going to do is calculate that Reynolds number. So we're going to calculate it based on the plate length. So that's Reynolds number based on L. We're going to U infinity L over nu, and we're going to put in our numbers. So we've got 1 meter per second for the velocity, 2 meters for the plate length, and then we need that viscosity for the air. That's the kinematic viscosity. We're going to look that up on a table. In order to look it up on a table, we need to know the temperature and the pressure. So we're going to assume standard temperature pressure using the NIST standard. That's the National Institute of Standards of the United States. And their standard temperature and pressure is 20 degrees C and 101,000 newtons per meter squared. You have to be a little bit aware that there are other STPs. I believe the International Chemistry Standard uses 0 degrees C here instead of 20, but most engineers use 20 degrees C and 101,000 as the standard temperature and pressure. When you look up the viscosity for that, you find that nu is equal to 1.5 times 10 to the minus fifth meters squared per second. So that's what we're going to plug in for our Reynolds to calculate our Reynolds number. So, all right, we're going to put those numbers in. So we get that the Reynolds number at the position, L equals 2 meters. The Reynolds number is going to be, when you plug those numbers in, Reynolds number based on L comes out to 1.33 times 10 to the fifth. So 1.33 times 10 to the fifth, nice big number there. Then we're going to plug that in to the delta over L expression. Delta over L equals 4.92, 1.33 times 10 to the fifth raised to the negative 1/2 power. When you crunch that right-hand side on your calculator, you end up with delta is equal to 0.0135 times L, where I brought the L over to the right-hand side. So delta is equal to 0.027 meters when I plug in that 2 meters. That is, it's 2.7 centimeters thick. So it's quite small. And this, remember, we said this was one of our assumptions was that delta would be very small compared to the length of the plate. And so we see that, in fact, the plate in this case is 2 meters long. The length of the thickness of the boundary layer is only 3 centimeters. So it's really 2 orders of magnitude smaller than the length of the plate. That is much, much smaller by our standard definition of that. An engineering definition, order of magnitude is smaller. 2 orders of magnitude is, hugely smaller. So the boundary layer is quite small. So the viscosity for flow over the plate, if you were to draw it, that's not anything like what it looks like. You'd have to draw it where this is 1/100th, the height of the plate, of the length of the plate. So it'd be very, very thin. So these viscous boundary layers and airflow in particular, they tend to be very, very thin, which is one of the reasons that you can use the assumption of not viscous effects when you're not near the plate. So things like the Bernoulli equation can be used up in this region where you're not in the viscous region.